welcome you all in this course on mechanical measurement system. Today we will continue to discuss on thermocouples, then we will discuss the working of RTDs and thermistors. So, regarding thermocouples, we will start with the laws of thermocouple. The working of thermocouples is governed by certain laws, right? And the first law of thermocouple is, if there is a thermocouple having junction 1 and 2 and depicting the temperature T1 and T2, and these two junctions, they are two dissimilar wires. Let us depict another one with red. So, these wires are of two different materials, and let us name them A and B, and the junctions are at two different temperatures, right? And it will definitely show some EMF. Some EMF will be developed, and which EMF can be noted with the help of a voltmeter, right? And this is EMF is of the order, normally is the order of a few microvolts. Now, suppose I increase at this portion of the wire, I increase temperature T3, this portion T4, this temperature portion T5, this portion temperature T6. Will it affect the output? As per the first law of thermocouples, output will not be affected, or temperature measurement will not be affected for any change of temperature in the conductor connecting between T1 and T2. So, this is the first law of thermocouples. Now, the second law. Second law states that in a thermocouple having wire A and B, having wire A and this is B, and a third metal is inserted, C, this is C, and again the entire system is at different temperatures. This part is at a particular temperature, this part at a particular temperature, it will not affect. The third metal C is inserted, the output will not be affected till these temperature as these two junctions is same. It does not vary. If this temperature is remaining same and we are inserting a third metal, these temperature as these two junctions is same, the performance of the thermocouple will remain unaffected, or output of the thermocouple will not be affected. Now, instead of adding a material here, C, right? These are the two suppose connected wires. If we add material C here at T1, a wire of material C is connected. This is C, right? Then, as long as the temperature as these two junctions is same, the change in the temperature or the presence of this C will not affect. It means I have a thermocouple. This is a substrate where I am doing the temperature measurement. So, instead of making a junction, I just weld two wires separately, right? But these temperature as these 2 points is same. When the temperature as at these 2 points is same, the output of the thermocouple will not be affected, or performance of the thermocouple will not be affected. That is I think this is third law. The fourth one is simply the law of addition. It means EMF generated for a given temperature difference, EMF generated for metal A and B, and EF generated metal B and C will be added if we are using a thermocouple made of metal A and C. So EMF generated by A and B and EMF generated by B and C shall be added when we measure the temperature using the dissimilar materials A and C. Similarly, if T1 and T2 they cause EMF E1 and T2 and T3 they cause EMF E2. So EA, suppose this is EB. Then T1 and T3 will cause EMF EC, and EC is equal to nothing but EA plus EB. This is law of addition. Now, using this law, nowadays when we measure the thermocouple the temperature with the help of thermocouples, all the tables which are available between the relationship between change in temperature and change in the microvolt output of the thermocouple, they have one reference temperature 0 degree centigrade. So it is always assumed that one end of the thermocouple it has 0 degree centigrade, and this end is at temperature T. But in actual practice, practically always maintenance of this temperature 0 degree centigrade, it can be maintained, but it is a tedious job. Means always you will have to replace the ice, because this 0 degree centigrade will be maintained with the help of distilled ice made out of distilled water, and in a flask or in an insulated flask you will have to keep this pool of water, and this end will be put into this flask, but it is some arrangement has to be made. Nowadays in most of the data acquisition systems there is an isothermal terminal block. So in isothermal terminal block, one end of the thermocouple is just simply used for measuring the unknown temperature T. Other end is connected to a block which is known as isothermal terminal block, which the temperature of this block remains constant. And thermocouples, and you can add number of thermocouples, okay, 5, 10, 20, 30 depending upon the design of the block, right? And this block remains at room temperature, let us say 25 degree centigrade. It can automatically detect also, or you can fix this temperature as 25 degree centigrade. Now, from 25 degree centigrade to 0 degree centigrade, this EMF is automatically added in the output of thermocouples. So we don't require actually the reference temperature of 0 degree centigrade. So EMF equivalent to this 0 degree centigrade and the room temperature is added into the output of the thermocouples, and then final EMF is noted, and then final EMF is converted into the temperature. And this is how the temperature sensing is done in nowadays in modern in modern data acquisition systems. Second thing is, sometimes this often happens when we have to take the change in temperature. Suppose the fluid is flowing in a pipe, right? And the temperature change is only 1 degree centigrade, right? Or let us say 2 degree centigrade or 3 degree centigrade, let us say 2 degree centigrade, right? And fluid is entering from this side at temperature T1 and leaving from this side temperature T2. Microvolt meter, the sensitivity, the output is only, if it is 0.25 if it is sensitivity is let us say 25 microvolt per degree centigrade, so change in the voltage is going to be 0.5 microvolt. Now here we can make use of thermopile. In thermopile, the thermocouples are connected in series. In thermopile, suppose I have to take temperature difference between temperature 1 and this is temperature T2. Suppose I have to measure the temperature between T1 and T2, then I can make use of thermopile, let us say, of 3 thermocouples. So all thermocouples will be connected in series. So, okay, that is one wire, and another wire is like this, and this is a copper wire which is connecting to the system, and this is also a copper wire. This is copper wire, and now we have 3 junctions. This is also copper wire. So now this is copper wire I am depicting with blue. It has to be depicted by this will make a junction. So one junction to 1, 2, 3, 3 junctions here, and 1, 2, 3, 3 junctions here. Now it is a thermopile of 3 thermocouples, and here in this thermopile, suppose with one thermocouple the output was E, thermopile of 3 thermocouples will give output of 3E. So once we are getting output of 3, it means equivalent to 2 degrees centigrade, where we are getting 50 microvolts. Now we will be getting 150 microvolts. Voltmeter is same, absolute error is same. So definitely accuracy of the measurement will increase, and we can have a thermopile of 5 thermocouples, 10 thermocouples, depending upon the application. Now thermocouples are also joined in parallel arrangement. This is one thermocouple, suppose A, B, and this is second thermocouple. So B of second thermocouple, B and A. So this is B, A, B, right? So in this case, all A's are connected and all B's are connected. So thermocouples are not in series. In previous case, when we were making the thermopiles, we were connecting A, B, then A, B. They were all in series. Now all A are connected and all B are connected. Thermocouples are in parallel. The net output of the thermocouple will be average of the reading of all these thermocouples. This is going to be the average of the reading of all these thermocouples, right? This also improves the reliability of the measurement by thermocouples. Now, after the thermocouples, we will take up the discussions on RTDs. RTD is a very important device and very reliable device for temperature measurement, RTD. Now, RTD stands for resistance temperature transducer, right? And the working principle of RTD is the resistance changes with change in temperature. This is the working principle of RTD. And RTD can I mean, if you take platinum wire, the RTD can measure up to 1000 degrees centigrade. Accuracy of the RTD for low temperatures, it is 0.001, right? Or in fact, it can go, and for higher temperature, it remains 0.1. But 0.1 for 1000 degrees centigrade is quite high, right? So, and if we measure very low temperature, I mean, we can have the accuracy of the order of 0.001 also. And for high temperature, it is 0.1. Even if we take 0.1, if we go percentage wise, it is going to be 0.01% at 1000 degrees centigrade. So 0.01% of temperature measurement accuracy is quite high accuracy. The readings are, or the measurement is highly reproducible in RTDs. So we can reproduce the same reading if we, so the temperature, it means the temperature measurement is very reliable. So in RTDs there is a thin foil, and in this foil a constant current is passed, right? And the change in resistance is determined by measuring the voltage across the foil. As the temperature increases, the voltage increases, and the drawback of this RTD is, first of all, it is costlier than the thermocouples, and an electronic circuit backup is required for the measurement from RTD. This is the, only drawback of RTD. It requires a sophisticated instrumentation, right? And normally platinum is used as a platinum because platinum has a linear variation. If you look at the change in resistance, R by RO. So this ratio may be less for aluminum. If okay, on this we are going, let us say, up to 800 degrees centigrade. So it can go up to between 3 to 4 times in this range, but the variation is linear with temperature. If you look at copper, copper has better sensitivity than, but its temperature limitation, the temperature limitation or the temperature is shorter than that in the case of platinum. Sensitivity is more. In fact, what happens beyond 600 degrees centigrade, the copper is considered to be more linear than the platinum. Now, nickel is also used as a resistance material in RTDs. So nickel is non-linear. There, it is something like this. Linear to, then it's like this. So nickel is highly non-linear. So normally for the temperature measurement, but the temperature, this resistance variation is high. So sensitivity of nickel is high. Sensitivity of copper is higher than the sensitivity of this platinum. But platinum is a linear relationship and very, and the relationship between R and RO does not change with temperature much. So that is why platinum is used, and it can sustain high temperature also. If I have to go for 1000 degrees centigrade, I have no option but platinum to be used as a RTD. So platinum is normally, I'll write the working range. The platinum, it works between 190 to 800 degrees centigrade, minus 190 to 800 degrees centigrade. Copper is used minus 150. Copper is, melting point of copper is more than 900 degrees centigrade. But copper is not recommended beyond 250 degrees centigrade. Melting point of copper is high, but it is normally not recommended below above 250 degrees centigrade. Otherwise, and the nickel is recommended for 0 to 300 degrees centigrade. So copper has a limited temperature range, minus 150 to 250 degrees centigrade, though it has melting point of I think 960 or more than 900 degrees centigrade. Nickel is used up to 0 to 300 degrees centigrade because beyond 300 degrees centigrade it becomes non-linear. So due to linearity related issues, it is not recommended. But copper, if you are using up to 200 degrees and 250 degrees centigrade, it is highly stable and it has a longer life, because life of the sensor is also important. Platinum also we can go beyond 800 degrees centigrade or 1000 degrees centigrade, but the issue is life of the sensor, because the foil is very thin. So if it is persistently exposed to very high temperature, that may damage the coil. Now we can have a comparison between thermocouple and RTDs. So thermocouple and RTDs, first is temperature range. So RTDs have a limited temperature range of 1000 degrees centigrade. Thermocouple can go up to 1700, and some of the thermocouples can go up to 2200 degrees centigrade also. Exotic thermocouples can go up to 2200 degrees centigrade also. So plain thermocouple, I mean ordinary thermocouple is cheaper than an RTD, and RTD approximately 2 to 3 times costlier than a thermocouple. But if you go for the exotic thermocouple or a high temperature thermocouple, definitely their cost is higher than the RTDs. And accuracy and linearity and stability. And stability. Accuracy, linearity and stability, they are high for RTDs. Accuracy of the measurement is high. Their linearity, they are highly linear. And stability in RTDs are high. But they have finite size of, RTDs have finite size. So for very narrow passages, RTDs cannot be put, where we can put the thermocouples on those narrow passages. Now durability, the reliability, stability and durability. Thermocouples are more durable because it is simply a wire. So thermocouples are more durable than the RTD sensors. RTD cannot be grounded. We can have grounded thermocouples, but RTD cannot be grounded. So once it cannot be grounded, it has lesser response or lesser or slower response time in comparison to the thermocouples. So the response time of thermocouple is higher. Sorry, RTDs cannot be grounded. RTDs cannot be grounded. They cannot be grounded. Thermocouples can be grounded. So when thermocouple is grounded, it has lesser response time, or time constant is less. But as RTDs cannot be grounded, their response time is higher in comparison to the thermocouples. Now there is one more device which is very often used for temperature measurement. It is used for the controls also in electrical systems, that is thermistor. It is an acronym for thermal resistor. It is a thermal resistor. It is a semiconductor and it has negative temperature coefficient. It means when the temperature of thermistor rises, the resistance goes down. When resistance goes down, more current will flow into the thermistor. More current will flow is thermistor, again its resistance will go down. So, but this loop does not go up to infinity. It doesn't mean that the resistance will keep on reducing and the power will keep on increasing. So what happens, the steady state in a thermistor comes when heat generated by the thermistor is equivalent to the heat conducted to the surroundings. When all heat generated by the thermistor is dissipated to the surrounding, then a steady state is attained. And the temperature range of thermistor is minus 100 to 300 degrees centigrade. So higher temperature we can go up to 300 degrees centigrade. Nowadays we have thermistor which can go beyond 300 degrees centigrade, 600, 700 degrees centigrade. But a thermal thermistor, a thermal resistance type of sensor, can go up to, it can measure temperature in a range of 100 to 300 degrees centigrade. So minus 100 to 300 degrees centigrade. And they are manufactured by taking the sintered mixture of metallic oxides of magnesium, nickel, copper, iron or cobalt. So it is a sintered mixture of these metallic oxides, and the resistance also for, the thermistor can range from a few ohms to some, let us say, hundreds of kilo ohms, right? And the diameter of a thermistor can be 0.2 or 0.15 mm to, it can go up to 1.25 mm, right? And So initially the thermistor draws a very small current and it follows the Ohm's law till the heating starts. When the heating starts, the variation in resistance is highly nonlinear, and it is like R1 is equal to RO e raised to power, beta 1 by T1 minus 1 by TO. It is the variation in resistance is governed by this equation, and the value of beta is normally it's 3000 to 4000. It's often close to 4000, and the temperature range which is covered, it is as I said, minus 100 to 300 degrees centigrade. Nowadays there are special type of thermistors which can go up to 600, 700, even 1000 degrees centigrade can also be measured with the help of a thermistor. Now after the thermistor, we will go for high temperature. Now we have amply discussed about the low temperature measurement. Low temperature measurement means the temperature in the range of 1000 or 1500 degrees centigrade. Now in some of the applications, the temperature is quite high. In some of the applications, the temperature is, let us say, 4000 degrees centigrade or 3500 degrees centigrade. For example, space applications. Now, if suppose I want to measure 3500 degrees centigrade temperature. For such type of high temperature measurement, there is no direct contact type of measuring technique. We have to go for indirect type of measuring technique. For example, we want to measure a stream of gas which is at 3500 degrees centigrade. Now in this case, what we are going to do, we will have to use indirect measuring method. In this indirect measuring method, we will connect this to a cooling water system. Cooling water system. Cooling water will be entering from this side and leaving from this side. Cooling water will take away heat, and this Q can be measured with the help of mCp delta T. So this delta T is normally taken as in the range of 50 to 55 degrees centigrade, 50 to 60 degrees centigrade, let us say 55 degrees centigrade. And this is a vertical tube. Once we have the value of Q and we have the heat transfer coefficient at the surface, so we can always use Q is equal to HA delta T. And delta T is nothing but temperature of the gas minus temperature of the wall. Now, what about the temperature of the wall? We can't fix thermocouple there. So in order to find the temperature of the wall, we'll have to find the temperature of inner wall. Now inner wall temperature, we can't fix thermocouple there also, right? We can make use of some already established correlations. The Nusselt number is a function of Reynolds number and Prandtl number, right? From here we will calculate the Nusselt number, and from Nusselt number we will calculate the value of H. And once the value of H is known and bulk temperature is known, then Q is equal to HAI delta T. From here we can get the value of this delta T, and from this delta T is nothing but wall temperature minus fluid temperature, bulk temperature, right? Or we can fix, because the inside wall temperature is going to be much higher than the fluid temperature, right? So this is an indirect temperature measurement technique. This is an indirect temperature measurement technique. And another technique can be, instead of this, suppose high temperature has to be made, so we'll take one tube, a bigger tube, and there is a cooling system. And this tube is opened from this side. So there is a cooling system within the tube. The cooling water is coming in and is going out. Now, high temperature gases are entering from this side. So in this passage, these gases will be cooled down, right? And here we can fix a thermocouple. Here we can fix a thermocouple. Now we have thermocouples which can measure range up to, let us say, 2200 degrees centigrade. That is rhodium and iridium thermocouple. Rhodium and iridium thermocouple. Rhodium and iridium thermocouple can measure temperature up to 2200 degrees centigrade with 6 microvolts per degree centigrade sensitivity. There are other thermocouples also, tungsten rhenium thermocouples. Tungsten rhenium thermocouples, it can go up to 2760 degrees centigrade. They are all exotic thermocouples and they are very costly. And boron graphite thermocouples, it can go up to 2500 degrees centigrade, but these two have accuracy of 6 microvolts. This can have accuracy of 40 microvolts per degree centigrade. So these are all exotic thermocouples, right? And they are very costly. So temperature of the gas is reduced to this range through cooling of this passage, and temperature measurement is made, and through after that doing certain calculations, right? Doing certain calculations, we can find the actual temperature of the gas. Another method of the measurement of high temperature is that in the stream of the gas itself, if you put a thermocouple. So if you put a thermocouple in the stream of the gas itself, and this side there is a cooling air and used with and controlled with the help of a solenoid. So here we have inserted a thermocouple. Initially it is at 250 degrees centigrade. Now the stream of hot gases is coming, let us say at 4000 degrees centigrade, right? Initially the air is flowing over the thermocouple and it is stabilized at 250 degrees centigrade. When hot gases are coming, right, they will increase the temperature of thermocouple, right? And the response of the thermocouple is going to be something like this. Now what we will do, from 250 degrees centigrade, let us say the moment the temperature reaches 1200 degrees centigrade, we will open this valve. The moment we open this valve, high velocity cold air will come and it will cool the tip of the thermocouple, but we will come to know the trend of the rise of the thermocouple. And then using this equation, lambda d thermocouple divided by dt plus T thermocouple is equal to T of the gas, temperature of the gas. Now this equation can be used, lambda d plus 1 QO is equal to KQI. Right, QO is temperature, final temperature of thermocouples. Now from here we can take the rate of the rise of the thermocouple, temperature of thermocouple. Time constant is known. This is how we can measure, or we can determine, not measure, the temperature of hot gases. Now suppose temperature of hot gas, let us take some example. Temperature of hot gases is 3000 degrees centigrade, right? And lambda, let us take some value, is equal to 2.8 seconds. Time constant of thermocouple is 2.8 seconds. We limit the temperature, this 2000, the thermocouple temperature should not exceed 1000 degrees centigrade. So in this case, for how much time the thermocouple should be exposed to the hot gases? So it is always theta by theta I is equal to 1 minus e to power minus t by lambda. Now, theta is, the gas temperature is 3000 degrees centigrade. So, and it should not exceed 1000 degrees. So, minus 250 divided by 3000 minus 250 is equal to 1 minus e to raised to power minus t minus divided by 2.8. Now, from here you calculate the value of t and the answer is 0.89 seconds. This is all for today. Thank you very much.